Hi, Nicole. Have you got it yet?
Almost. I have some ideas, but I still don't know how to stack them yet.
What have you come up with then?
I think the concept should be simple. When we were little, we loved to stack blocks and make skyscrapers.
That's good. It's simple and regular.
Why don't you guess how I will stack the next column?
Okay, that's easy. The first column has 2 blocks. The second column has 4 blocks, 2 blocks more than the first column. The third column has 6 blocks, 2 blocks more than the second column. 2 blocks are added to each column, so the fourth column will have 8 blocks. Okay, it's my turn to quiz you now.
Bring it on.
Well then, what is the next one?
2, 3, 4, 5. For the next one, there should be 6 blocks on each side.
That's correct. Hey, Mr. Ko.
Hi guys, have you come up with any ideas for the background yet?
It's going fine. We're almost done.
We've been playing while thinking. Actually, I should say that we've been stacking while thinking.
I know, that's how you get inspiration, right?
Yeah, we're stacking them randomly. One person stacks a group of figures first, then the other person guesses what the next figure will be.
You're using blocks to show different sequences.
What is a sequence?
A sequence is a set of numbers arranged in an order. In a sequence, each number is called a term. For example, if a sequence has 4 numbers, then there are 4 terms. If these are 1, 3, 5, and 7, then the first term is 1, the second term is 3, the third term is 5, and the fourth term is 7.
I understand what the term of a sequence is, but what do you mean by numbers that are arranged in an order?
Put simply, that means that the numbers are arranged in an order according to a pattern. In a sequence, the order of the numbers is important. For example, 1, 3, 5, 7 is in ascending order, while 7, 5, 3, 1 is in descending order. These two sequences are not equal. Therefore, it's only when the number of terms is the same and the corresponding terms of 2 sequences are the same that we can then say the 2 sequences are equal.
A sequence is a set of numbers that are arranged in order. What does this have to do with our blocks?
We can use a sequence to represent the number of blocks in each group. The sequence that represents these 4 shapes is 2, 4, 6, and 8. And the sequence that represents these 5 figures is 3, 5, 7, 9, and 11. It's fun to find out the number pattern of sequences. It's similar to how you found out the pattern of the block figures just now.
Hey, Mr. Ko, since this is so fun, why don't we play together?
Sure, I have no problem with that. But let's also apply some mathematical concepts as we play so that we can work while having fun, shall we?
Yes, yes.
Let's look at this group of figures. What will the next figure look like? How many blocks should we use there?
Let me try. The first figure has 2 blocks of each color. The second figure has 3 blocks of each color. The third figure has 4 blocks of each color. So the fourth figure should be like this. 5 blocks of each color. 5, 10, 15, 20. I have used 20 pieces of blocks here.
Correct. How many blocks should be used if we stack the 100th figure?
Wait, wouldn't it be too big if we make it up to the 100th figure?
Exactly. The blocks here are not enough for us to make up to the 100th figure.
Instead of stacking to find the answer, we can calculate it.
Calculate it?
That's right. But before that, let me teach you more concepts of sequences first. The first term of a sequence is called T1. The second term is called T2. The third term is called T3, and so on. Take this group of figures as an example. The first term, T1, is 2. The second term, T2, is 4. That is 2 plus 2. The third term, T3, is 6. That is 4 plus 2, i.e. 2 plus 2 plus 2. The fourth term, T4, is 8. That is 6 plus 2, i.e. 2 plus 2 plus 2 plus 2. But it is hard to generalize the expression of the nth term. So we rewrite the expression as follows. The first term T1 is 2, that is 2 times 1. The second term T2 is 4, that is 2 times 2. The third term T3 is 6, that is 2 times 3. The fourth term T4 is 8, that is 2 times 4. According to the pattern of T1 to T4, we know that the nth term Tn is 2 times n, that is 2n. As an algebraic expression, 2n represents the nth term of the sequence, and 2n is called the general term of the sequence. We can use the general term of a sequence to find out each term of that sequence. For example, if n is equal to 15, we can find the 15th term of the sequence. The 15th term is 2 times 15, which is equal to 30.
Let me try to work out the general term of the sequence for this group of figures. The first term, T1, is 3, that is 2 times 1 plus 1. The second term, T2, is 5, that is 2 times 2 plus 1. The fifth term, T5, is 11, that is 2 times 5 plus 1. According to the pattern of T1 to T5, we know that the general term Tn is 2 times n plus 1, that is 2n plus 1.
As I just said, we can use the general term of a sequence to work out each term of that sequence. In finding one term, we'll work like a number machine. A number machine is pre-installed with a general term of a sequence, such as 2n. If we enter n equals 1, the output of the first term, T1, will be 2. If we enter n equals 2, the output of the second term, T2, will be 4. As long as we enter a value for n, a calculation will be made. That is, by calculating 2 times n. The number machine will output the nth term, Tn, of the sequence. For example, if we use a number machine to work out the 8th term of the sequence, the process would look like this. First, enter n equals 8, and then calculate 2 times 8. That is 16. As a result, the 8th term, T8, is equal to 16. Now let's get back to the stacking of blocks. With our understanding of sequences, we can work out the number of blocks we need to build the 100th figure.
First, we need to deduce the general term of the sequence. Then, we can use the general term to find out the 100th term of the sequence. The first term, T1, is 8. That is 4 times 2. The second term, T2, is 12. That is 4 times 3. The third term, T3, is 16. That is 4 times 4. The fourth term, T4, is 20. That is 4 times 5. We would rewrite the expression as follows to find the nth term easier. The first term, T1, is 8. That is 4 times 1 plus 1 in brackets. The second term, T2, is 12. That is 4 times 2 plus 1 in brackets. The third term, T3, is 16. That is 4 times 3 plus 1 in brackets. The fourth term, T4, is 20. That is 4 times 4 plus 1 in brackets. The general term, Tn, is 4 times n plus 1 in brackets. When n is 100, the 100th term is 4 times 100 plus 1, which is 404. Therefore, the 100th figure will have 404 blocks.
Correct. We can use different sequences to represent the number of blocks in each group. The first sequence is 2, 4, 6, 8, and so on. The second sequence is 3, 5, 7, 9, 11, and so on. The third sequence is 8, 12, 16, 20, and so on. Did you notice that these few sequences have something in common? Observe the pattern between the numbers again.
From the first term to the second term, the second term to the third term, the third term to the fourth term, and so on and so forth. We get the next term by adding the same number. In the first sequence, 2 was added. In the second sequence, 2 was added. In the third sequence, 4 was added.
We can also put it this way. In a sequence, from the second term onwards, the difference obtained when we deduct any term from its previous term is the same. This is called the common difference. This type of sequence is called an arithmetic sequence.
Mr. Ko, are there any other examples for illustration?
Sure. For example, if the first term of a sequence is 5, and from the second term onwards, the difference between any term and its previous term is -3, this means that the common difference is -3. The first term is 5. The common difference is -3. The second term is 2. The third term is -1. The fourth term is -4. 5, 2, -1, -4, and so on. This is also an arithmetic sequence.
Are there any other special sequences?
Yes, arithmetic sequences are just one of the commonest sequences. There are also geometric sequences. I can use an example to show you what geometric sequences are. It's also related to figures. Let's take a look at this figure. We have a solid triangle here. By joining the midpoint of the sides of the triangle, we can divide it into 4 small triangles. When we take the middle small triangle out, we will have the second figure. Repeat the above procedure for all the solid small triangles. That is, take out the middle small triangles, then we will have the third figure. If we continue to repeat the above procedure, we will make a series of figures. These 5 are the first to 5th figures. This series of figures is called the Sierpinski triangle. It was proposed by a Polish mathematician, Sierpinski, in 1915. If there is a sequence that represents the number of solid triangles in every figure of the Sierpinski triangle, can you work out the first to 5th terms of the sequence?
First, we need to consider the changes of the figures. The change from one figure to the next is actually a change from one solid triangle to 3 small solid triangles. The first term is 1. That means there is 1 solid triangle. The second term is 3. That means there are 3 solid triangles. The third term is 9. That means there are 9 solid triangles. When a solid triangle becomes 3 small solid triangles, the number of solid triangles is multiplied by 3. According to this pattern, the second term is T1 multiplied by 3. The third term is T2 multiplied by 3. Then, the fourth term is the third term multiplied by 3. This makes it 9 times 3, which equals 27. Then, the fifth term is the fourth term multiplied by 3. This makes it 27 times 3, which equals 81.
Correct. In the Sierpinski triangle example, from T2 onwards, each term is the previous term multiplied by 3. In this example, any 2 consecutive terms have 1 fixed ratio. This is called the common ratio. In sequences, if any term from T2 onwards gives the same result when divided by the previous term, this type of sequence is a geometric sequence. Let's play one more game. Let's use blocks to explore 2 special sequences. Look at this group of figures. I have already made the first to 4 figures. There is a sequence that can represent the number of blocks needed to make this group of figures. Let's work out the general term of the sequence first.
The figures are squares. The first term, T1, is 1. That is 1 to the power 2. The second term, T2, is 4. That is 2 to the power 2. The third term, T3, is 9. That is 3 to the power 2. The fourth term, T4, is 16. That is 4 to the power 2. According to the patterns in T1 to T4, we can determine that Tn is n to the power 2. Therefore, the general term of the sequence is n to the power 2.
This sequence is called the sequence of square numbers. Each term is a square number, 1, 4, 9, 16, and so on. Besides square numbers, let me show you another group of figures. The number of blocks that make up this group of figures can also be represented by a sequence. Let's look for the pattern there and work out the fifth term of the sequence.
This time, the figures are triangles. The first term is 1. The second term is the first term plus 2. The third term is the second term plus 3. The fourth term is the third term plus 4. Therefore, the fifth term is the fourth term plus 5. That is 10 plus 5. This is equal to 15.
This sequence is called the sequence of triangular numbers. Each term of the sequence of triangular numbers is a triangular number. 1, 3, 6, 10, 15, and so on.
The sequence of square numbers and the sequence of triangular numbers, they're easy to remember. We just need to remember the two groups of figures.
There is also a very famous sequence which is related to the growth of plants and animals. In 1202, the Italian mathematician Fibonacci published a book on mathematics. In the book, he raised a question about rabbit breeding. There were 4 assumptions. 1. In the first month, a pair of female and male rabbits are born. 2. The rabbits become mature after 2 months and can breed. 3. Every pair of mature rabbits will breed a pair of female and male rabbits every month. 4. The rabbits will never die. Based on these assumptions, we can work out the number of pairs of rabbits there are every month. This series of numbers forms a sequence known as the Fibonacci sequence. Based on the first assumption, there will be 1 pair of rabbits in the first month. The first term, f1, of the sequence is 1. In the second month, the rabbits that were born will still exist. According to the second assumption, this pair of rabbits is not ready to breed. Therefore, there is still 1 pair of rabbits. The second term, f2, of the sequence is also 1. In the third month, this pair of rabbits is now 2 months old. They're mature and can now breed. For easy identification, let's use grey rabbits to represent mature rabbits. In this month, there will be a pair of newborn rabbits. The new number of pairs of rabbits should be the original number plus the number of newborn rabbits. The total number of rabbits is now 2 pairs. F3 is 1 plus 1, which equals 2. In the fourth month, let's look carefully at the pattern of the changes in the number of rabbits. The total number of pairs of rabbits equals the original number of rabbits plus the number of newly born rabbits. The original number of rabbits is the number of rabbits of the last month. The number of newly born rabbits, that is the number of mature rabbits, is the number of rabbits in the last 2 months. Therefore, F4 is equal to F3 plus F2. 2 plus 1 equals 3. Actually, when n is larger or equal to 3, fn equals fn minus 1 plus fn minus 2. We can use this formula to work out the third term and the subsequent terms. f5 is equal to f4 plus f3. 3 plus 2 equals 5. f6 is equal to f5 plus f4. 5 plus 3 equals 8. f7 is equal to f6 plus f5. 8 plus 5 equals 13. In fact, the Fibonacci sequence can be easily found in nature. For example, the number of petals of some flowers and the number of branches of some trees match the Fibonacci sequence.
Oh yes, I can add the number of flower petals that match the Fibonacci sequence to my design too.
Impressive! You're able to apply mathematical principles to your design. Come on, tell me more about your idea. Let me see how I can help.